I'm Jason Herbert, and over the last 2.5 years of this podcast, we've had people from every single walk of life that you could possibly imagine, and we've had some amazing people. We've had Pulitzer Prize winners, we've had Oscar winners, Emmy winners, writers, directors, historians, astrophysicists, you name it, they've been on this pod. But we haven't had a Nobel Prize winner, and we've never had anyone who's worked on the Hubble Space Telescope until today. Today, we bring on for you two amazing scholars. I'm talking about Dr. Jack Szostak and Dr. Mario Livio to talk to you today about the quest, the search for extraterrestrial life. We're looking for signs of intelligent life out there, and if you're like me and from Florida, you know just how difficult this could be. So, Jack is a chemist and Mario is an astrophysicist, and together not only do they fight crime, but they look for life in other places. And they just co-authored a brand new book called Is Earth Exceptional? The Quest for Cosmic Life. And we have an amazing conversation lined up for you today, talking about how we search for the things beyond this planet. How do we know what we know? And do we hope for life out someplace else? And why does all that matter? So it's a great conversation with two amazing scholars who I am so proud and delighted to now call my friends. I hope you enjoy this conversation. Sit back and relax. Reckoning with Jason Herbert starts now. We're live now, so we'll get going. Mario, I have to tell you a thing. I got into history because I did not like mathematics at all. And all of a sudden, I'm reading this book, which has astrophysics and chemistry. And I'm finding that there's this horrible problem, which is that I absolutely love reading this book. You and I were just talking before we started recording. This is sensational, Mario. I really, really love this book.
I'm glad you think that. We, of course, put a lot of effort into this book, and we like the outcome.
Yeah. Before we started recording, you and I were talking about, there's actually quite a bit of a level of sophistication to this particular book. Everybody who's listening in, we're talking about Is Earth Exceptional? The Quest for Cosmic Life. Mario, you're the co-author here. One of the things that I very much liked, and this doesn't always happen with trade presses, is that this book is designed towards a general audience, people who are interested in the world around them. But you're not lowering the bar for anybody here. You're asking the reader to do some work.
You're right. If somebody asked me, is this book for everybody? I would say, no, it's not for everybody. It's for educated, readership. And in particular, it is for people who are interested in this subject. If you are not interested about, how did life start on Earth, or is there life elsewhere, then this is definitely not the book for you. If you are interested, then presumably you are also willing to put in a little bit of effort, to follow up. We still, there is nothing that is conceptually extremely difficult in this book. It is just the fact that, when you talk, for example, about biochemistry, the names of the compounds are horrible and the name of the processes are also complicated. So people, get sometimes intimidated by this. But they shouldn't, because we try to emphasize, what are the thought processes, what are the problems people were trying to solve, and emphasize those.
Yeah, and frankly, I really enjoyed the approach. And you're absolutely right. So some of the chemical compounds and things like that are challenging. But again, if you've got a love of learning, that challenge is the thing that I greet, because I'm like, I've never seen that's a lot of syllables on, but that's okay. Before we get going here, before we start talking about the book in depth, do you want to introduce yourself and talk about who you are and what kind of work you do?
I'm Mario Livio. I am an astrophysicist, which means a theoretical astrophysicist. I worked for 24 years with the Hubble Space Telescope. And my training originally was in physics. I am a fellow of the American Association for Advancement of Science. And I've written 8 popular science books. This is the 8th. It's just appeared September of last year. And this one was written together with Jack Szostak, who was a Nobel laureate in physiology or medicine.
Yeah, there is so much, Mario, in this book. I want to ask you, and I worried when I started reading this book. It's like, how am I ever going to only talk to him for an hour with this? Because I've got so many questions. And you're right. I feel like so many. If you can see the Star Wars toys above my left shoulder, I think that so many of us are drawn to the stars in some form or fashion. And I really appreciated being able to chance to read this book. I guess one of the questions I want to ask you, first and foremost, I keep thinking of the great Arthur C. Clarke quote, which says there are really 2 possibilities. Either we are alone in the universe or we are not, and both are equally terrifying. Can I ask you, does it matter if we are alone in the universe or not? Like, why are we drawn to this question?
To me, it certainly matters. I will tell you. Look, being the life on Earth is our last bastion of being special in a certain way. Namely, we have not yet found life elsewhere. And you might have thought that I would like to be something so unique. The fact is that no, I don't. Actually, I think that's kind of arrogant to think that we are the only life in the universe. And as a result, I actually would like to think that there is life elsewhere. Now, one has a little bit to distinguish between very simple forms of life and complex, or what we call intelligent life.
Mm-hmm.
And, I cannot tell you that I'm sure that there's lots of places with intelligent life, but I will be amazed if there isn't simple life in many other places, even though we have not found yet any. And this is why we actually have to search for it. Oh, and I see now that Jack has joined us too.
Well, speaking of intelligent life in other places, Jack, how are you, sir?
I'm good. Can you guys hear me?
Yes.
We sure can.
Okay, good. Sorry, I got held up, and then I had to figure out Chrome, which I never use.
Please. We were just I was just talking with Mario about really the central question here, which is, does it matter or not if there is life elsewhere? Why are we concerned with this question? Just a small one.
Yeah, I think it's a big question, right? I mean, I think almost everyone would like to know if we're alone in the universe or there's life out there, and yeah, I don't know. That seems like a big question to me, so makes me curious.
Let me add something to what I already told you, and that is the following. You see, Jack is trying to produce life in his lab. If we actually knew that life is ubiquitous, that there is lots of life in the universe, that would mean that would encourage him in his type of research.
Yeah.
That would mean that, okay, nature could do it, so I can try to do it too. So that's another reason why, we want to know whether it's life elsewhere.
Yeah. No, that's really true. I mean, at the moment, we have no idea how hard or easy it is to get life going. So just seeing even one independent example would be enough to convince us that it's just not really that difficult.
Yeah, I want to ask the two of you, because you both come from different fields here. And actually, let me just back up just a little bit. Jack, do you want to introduce yourself to the audience and tell us who you are and what you do?
Yeah, sure. I'm a professor in the Department of Chemistry at the University of Chicago. I've worked on a bunch of different things over my career, but the last 25 years, I've kind of gotten hooked on this question of the origin of life, and so our approach is really an experimental one, in the sense of trying to build life in the lab and thereby understand all the steps that you need to go through to go from simple chemistry to primordial forms of life. Ultimately, we think that'll give us some insight into how life got started on the early Earth.
You know, I was thinking before we recorded, I was looking at all of our Vitas, and I was thinking about a very simple idea, which is essentially this podcast today is the punchline, is the starting point to a joke. It is a chemist, an astrophysicist, and a historian all walk into a bar. And
it would be nice to do that right now after a faculty meeting.
I'm sure you're ready. And, I got to thinking about that as a joke, but then I actually started to think about the role of each of our own careers. And ultimately, this does seem to be more than not a question of understanding what it means to be human. These searches maybe for extraterrestrial life, so forth. What is this? Mario was just talking about. What does this say about ourselves? Are we still special if we're not the only only ones on the planet?
Yeah, you're absolutely right. I mean, it's also a question of origins. I mean, Jack and I kind of agree that the most important questions still remaining open in science all have to do with origins, namely, how did the universe start? How did life start? And maybe ultimately, how did consciousness start?
Mm-hmm.
We have made enormous progress in the first two questions. I mean, they are not completely solved. There are many, many remaining questions. But, we know a lot compared to, let's say, 50 years ago in both the origin of the universe and the origin of life. I actually have a feeling that on the origin of consciousness, we are somewhat behind still. And I say this because I actually recently saw somebody interviewing 5 people dealing with consciousness, and each one of them came up with a completely different theory. When there are 5 theories, it means that there is no convincing theory at the moment.
I want to ask you about this book and about looking for life beyond the bounds of, say, Earth or even our own solar system, which is, Jack, you're a chemist. Mario, you're an astrophysicist. How do we begin to look for life beyond the Earth? Like, what are the approaches? What do we do? Are we listening? Are we looking? Are we testing in a lab? Like, how do we do this?
Well, it's like a 4-pronged attack on this problem. One is the one that Jack is taking, which means trying to understand how life here began. And he's trying to do that by trying to actually produce life in his lab. A second approach says looking for life in our own solar system, which means, there are lots of things that landed on Mars, orbit Mars, and so on. There have been already some searches in Venus, and there are planned some searches in moons around Jupiter and Saturn. In particular, one was launched just last October, the Europa Clipper, which will search for, potential life on the moon of Jupiter. Then there is the search for life on planets revolving on stars other than the sun. And that is done by trying to determine the composition of the atmospheres of these planets. And finally, there is the search for so-called intelligent life by looking either by listening, namely in radio and electromagnetic radiation, or like lasers or things like that. So that tries, and also looking for potential artifacts of such civilizations, that maybe they once visited Earth or whatever. So all of these are happening in parallel. And with some luck, one of them will get us there first.
there's a question here that I wanted to ask you that you posed early in the book. The idea of chicken or the egg. We asked this idea of, and you're using this metaphor here of the idea of chicken or the egg. And I kept thinking about the idea of maybe chicken and the egg, as far as which comes first. The way that things were being posed to me. Do you guys want to talk a little bit about this idea and how you're trying to use this commonly understood thing as a way to understand life in the universe?
Sure. I mean, when it was hard to come up with any reasonable model for how life got started, right? That's when this sort of paradox was expressed. But I think we have a completely different way of looking at it now, right? As a continuous pathway, going all the way from planet formation to understanding the conditions on the early Earth, understanding the chemistry that can start to go on in different environments early on. And then we're getting more and more insight into how you build up more complicated molecules. And then what we're looking at in my lab is how these more complicated molecules start to come together and assemble into bigger structures that look more like a cell. And once we understand a few of the next steps, how this primordial cell can grow and divide, replicate its genetic information, that to me, that would be life. And then life starts to evolve and become better adapted and more complex. And then the next thing you know, here we are, right? So there is no more chicken and egg paradox in that view. It's just a continuous pathway, which, I think makes a lot of sense.
I kept thinking as I was reading the book about these moments, almost like this spark of life, like what happens. And I kept thinking about something on some other planet, some exoplanet, some moon orbiting some star, some other place. And I guess, Jack, is that what's going on in your labs now? Is that you're just trying to push these molecules together to see if something happens? Like, what is the general idea? I mean, as I'm trying to imagine, I was telling this to Mario before we started recording. I went into history before because I didn't like math at all, and now all of a sudden I've got your book in front of me, trying to understand this world and the worlds around me. So, what happens in your lab? How do you test to see how life begins?
Well, so one thing is we don't have to push the molecules together to make them start to do something interesting. The right kinds of molecules just like to assemble into bigger structures. So, for example, soap molecules assemble into membranes spontaneously because it's a lower energy state when they do that. Of course, that only happens in the right environment, in the right conditions. So a lot of what we're trying to do is figure out what are the right molecules, what are the right environments and the right conditions so that it will just happen spontaneously.
And I guess maybe that kind of gets to some of your work, Mario, as far as what is the right environment. So much, I get so excited because of my own childhood, the Star Wars stuff behind me, the idea, the quest, right? My vivid imagination as a child, wondering where are these other planets like Earth, right? Do they exist?
Right. So, until 1995, we didn't know of a single planet around a sun-like star. In 92, we discovered some planets around an object that's very bizarre called the neutron star, but life cannot be there. In 95, we discovered the first planet around a star that is more like the sun. At this point now, we have discovered more than 5,800 confirmed planets around sun-like stars. And in fact, you can sort of extrapolate to the whole Milky Way galaxy, and you can have numbers in the hundreds of millions of planets. Well, not quite like the Earth, but, sort of in that ballpark, orbiting stars that are somewhat like the sun. So there is no, I would say, shortage of real estate in terms of where life can start. Now, of course, there are differences among these different planets and so on. And in fact, to be frank about this, we have not yet discovered what one might call Earth 2.0, namely a planet that is exactly like Earth and is orbiting the sun exactly like the sun. That we still don't have. But we have lots of planets that are, well, around the smaller star typically, so they are closer in, but they receive the same amount of energy from their star, and they are rocky, like the Earth, and so on. So we have all of that. All of that we do have. Um, Sadly, a number of the best candidates proved not to have an atmosphere at all, but that's partly because they are around stars that are smaller and therefore are very active when they are young. They can strip planets of their atmospheres. But uh, I have no doubt that there are places that have the conditions that, in principle, can allow life to begin. In practice, it's a different thing altogether because it still depends on many processes that had to happen all at once, at the same time, in the right order, and so on.
I actually want to ask you. I want to ask the two of you to go back in time to say 1994, when we were all much younger men. And I want to ask you about the mindset as scientists. Mario, you say we did not know for certain about these planets prior to, say, 1995. Was that more of a situation where we really thought they were out there but just couldn't prove it? Or as a scientist you go, we just don't know until we find it? What's the mindset? Because I want to know basically the idea, and for yourself as well, Jack, is like, just because we haven't done it yet doesn't mean it's not possible.
Sure.
You know.
Yeah, I think until we see it, we don't know. But I would have been amazed if we then discovered that there are no other planets, because we know that the laws of physics uh, are the same throughout the universe, and we know this because we look at galaxies that are 10 billion light years away, and we see that the same laws of physics apply. So. It would have been amazing if planets didn't form that were somewhat like Earth around other stars.
Yeah, so back then there were several groups that were starting to look for planets, but it's not easy technology, right? So it took a while to develop, and I think there was the idea that to detect an Earth-like planet, that takes at least a year to go around its sun. I mean, that would take a lot of observations, very, very sensitive over a long period of time. And so it was really surprising when the first confirmed exoplanet had a much shorter orbital period, just a few days, which actually made it much easier to detect. But that kind of opened the floodgates, right? Once there was that first example, then right away people started to broaden the search and look for things with longer orbital periods and smaller masses, and that to do that, to see planets like ours around, with like a year or more orbital period around a sun-like star, takes such sensitive technology. I mean, it's still pushing the state of the art.
Can I ask you, when we are looking for signs of life, and I'm definitely not talking about my teenager right now who is in his own galaxy as I'm trying to get him ready for college, or at least self-awareness. But what are we looking for? Like, what are the necessaries for life to exist anywhere?
So, to say this very simply, I would say we're looking for atmospheres of these planets that are out of thermochemical equilibrium. It's a little bit like You cannot have a situation where you have a room full of grad students and lots of pizzas there, and for that state to remain there. It doesn't happen. So, in the same way, if you find an atmosphere that is, for example, very rich in oxygen, let's say, more than 20% oxygen, and at the same time, it is rich in methane and so on, that cannot happen from simple chemical processes. On Earth, that can happen because the life processes introduce this disequilibrium. So, situations which are characterized by this kind of thermochemical disequilibrium, they are the ones that are probably the best signs of biosignatures. I mean, signs of some form of life doing its thing there. Now, you can then break this into a variety of things that you want to see. But for example, a very high concentration of oxygen is by itself quite telling, because even in the Earth's atmosphere, the oxygen that is in the atmosphere was formed by life.
Yeah, and that's actually also one of the easiest things to detect as a potential sign of life. But no one sign of life, such as oxygen, is enough by itself, right? It turns out there are other ways, in theory, of making an atmosphere that has a lot of oxygen. So then you'd want a second line of evidence. So something like the simultaneous existence of methane, which above a certain level might be a sign that it's actually the methane's also generated by living organisms, like it is on our planet. But again, there are other ways to make methane. So then you'd want a third and fourth line of evidence to be increasingly sure. And you also have to couple that with knowing as much as you can about the planet, right? How big is it? What's its gravity? How much water is it likely to have? What's its average temperature going to be like? Because you don't want it to be like boiling hot or freezing cold all the time. So we have to go after all of these separate lines of evidence. And as we get more and more of those, we would get more and more convinced.
Right, and just to add one thing, you were looking typically for planets that are in what is called the habitable zone of their star. This is that region of range of distances where the temperature is neither too hot nor too cold, but rather such that it allows for liquid water to exist on the surface, because we think that liquid water is a necessary solvent to actually allow for life to start.
Yeah, I guess maybe a good example here might then be to talk about what we know about life on Earth. Because I think that this, I grew up, gentlemen, in a devout Southern Baptist home in Western Kentucky, as you can probably imagine, before moving away from all of those things. And, religion told us one thing and science told us something else entirely. So I'm kind of wondering, can you, in a matter of moments, can you explain to us how life evolved here on Earth?
So, okay. So my view is that it's a completely natural process, right?
Okay.
There is nothing in anything we have seen so far that requires any unnatural, supernatural, religious, or other explanation, right? So really, what we need to understand is the physics and the chemistry of planet formation, planetary environments. What are the chemical reactions that are going to happen that will give us the right starting set of molecules? So we can get to something as complicated as RNA or DNA, which can store and transmit information. Right? That's what we have to understand. All life on Earth now uses DNA to store its information, uses RNA, which is a fairly similar molecule, to do a lot of other jobs in the cell, including the synthesis of proteins, which do most of cell functions. So we want to understand all these chemical steps, and it's like cellular life that we see now it's quite complicated, right? Every cell has thousands of chemical reactions going on, thousands of enzymes. Um, so we need to understand how you can get there from really simple beginnings. That's a lot of what we're trying to do in the lab.
And I would say that they are definitely about halfway there, in the sense that like if you look at something like RNA, the building blocks of RNA have these nucleotides. They already found ways to make 2 out of the 4. Okay, natural ways, simple. And what's more amazing is that the same chemistry that does that can also form 12 out of the 20 building blocks of proteins, which are the amino acids that can make that. And also the precursors of all the things needed to make the membranes of cells and so on. So, the people in the origin of life community, they are more than halfway there, in terms of showing how from the basic laws of chemistry you can get the molecules of life.
Yeah.
So I'm guessing
there are, it's not to say that there aren't some gaps in our understanding, but those are the current exciting research areas, right? And so those gaps in our knowledge are what sort of attract our attention and our effort. And really, over the last 10 years, the progress has just been accelerating. So I think we'll understand how to get to all the right molecules fairly soon. And then I think we already have a good understanding of how to build up the larger structures, the cell membranes, the genetic polymers like RNA. And then getting everything to work together and figuring out the right sources of energy. That's also something we're starting to work on. But, it's getting figured out step by step.
You talk in the book about this giant asteroid that smashes into the Earth at one time. But I wanted to ask you this: like the idea of, I'd always, these ideas like where does life come from and things like that. I think there's the idea here in the book about the links between, say, the evolution of life and the evolution of Earth itself. You point pretty heartily to the idea that life evolves here on Earth and does not come from some other place, being delivered in the form of a cell that travels on an asteroid somehow and so forth. Am I correct?
Yes. Yeah. I mean, that idea won't go away, right? It's called panspermia, and it's been around for a long time.
Yeah.
It doesn't really solve any of the interesting questions, right? Even if life started,
it just pushes the problem elsewhere.
Back, right? So,
it sounds like Congress. So
it just pushes the problem elsewhere.
Yeah.
I mean, this is not to say that asteroid impacts and things like that did not play a role in the origin of life on Earth. They definitely did. They may, for example, transform the composition of the early atmosphere of the Earth into something that was better at, generating the beginnings of life, for example.
Which, for example, if I can just chime in here, when you have one of those giant impacts, the atmosphere changes in a way that makes it much easier to synthesize large amounts of cyanide. And this is just one of the things I love about this early chemistry, right? Here you have a molecule that's like a terrible poison now, but it's a molecule that carries a lot of energy, and it's a great starting point for building all of the molecules of life, the nucleotides, amino acids, and so on. So, yeah.
Because it has carbon and nitrogen already in it, which are needed.
Yeah.
I want to ask you, Mario and I were talking earlier today about how the evolution of this own podcast itself really started off as a movie and history podcast, and as continually, it's about to get a new name here in a matter of months. But because of that, we see so many films devoted to Mars itself. So
Yeah.
I want to ask you about Mars. Elon Musk is talking about traveling to Mars, which tells me that we will still be devoid of life on Mars. But can we talk about the search for life on Mars and why Mars is so
Yeah.
intriguing?
Sure, yes. Yeah, look, Mars is the nearest planet, and it formed from the same part of the initial material that formed the Earth, roughly. So, so at some point, maybe 4 billion years ago, it probably had conditions that could have allowed life to emerge, at least. Now, since then, life is a smaller planet, so it lost its heat, it lost its atmosphere. Now it just has a whiff of an atmosphere. But there is no reason. So it would be amazing to me if there is some present life on Mars. But past life was definitely possible. We know there is lots of evidence that there was liquid water on the surface of Mars. We can see streams, deltas of rivers, and things like that, lakes. Um, and even today, by the way, there is lots of evidence for liquid water underneath the surface, deep underneath the surface of Mars. So there is every reason to believe that there could be evidence for past life on Mars. Now, I want to remind you that even during my lifetime, there have been 2 times when there were already claims that life was found on Mars. One was the Viking landers, where there was an experiment that mixed some Martian soil with some nutrients, and they thought that they saw some metabolism. The other was an asteroid that came from Mars to Earth, and was shown to have some internal structure that mimicked fossilized life. Both of those turned out not to be correct. So life was not found yet on Mars. However, for example, the Perseverance rover, which is currently on Mars, collected lots of samples, put it in boxes. They are scattered on the surface of Mars. And with some luck, in 2030 or thereabouts, some mission will actually bring those samples back to Earth for further analysis. So there are good reasons to think that we will try to find, whether there is evidence for past life on Mars.
But I think something that's a little further in the future, but I think is what will really be needed to nail this down is to be able to drill down below the surface, right, into those reservoirs of subsurface water. If there's any remaining life on Mars, that's where we would find it. That's a lot harder to do, so it'll take a while. But I wouldn't be terribly surprised if there were some simple, like, bacterial forms of life in subsurface water on Mars. If we do find that, my bet would be that it will actually be closely related to the life we're familiar with here on Earth, just because there was so much exchange of material between Earth and Mars early on as a result of large impacts.
Wow, I hadn't even thought about. Okay, one of the things you also talk about is not only Mars, but within our own solar system, the idea of looking at some of the other moons as well. I know that some of the moons have tremendous bodies of water. Am I correct? But you would have to drill down to get to them. Is that correct?
Yeah. Well, to drill through them is not easy because there are miles of ice. But in cases like, for example, Enceladus, which is a moon of Saturn, we can see plumes that come out from the surface, which means that the ice is cracked. And so instead of digging all the way through the ice, in principle, some orbiter could fly through the plumes and determine the composition of those plumes and find out what's going on with those. There is one point that Jack and I emphasize in the book, which is that we don't think that oceans are the best place to start life, for life to begin. But if you bring life to an ocean like this, maybe you can sustain the life. So in principle, for example, if a rock with some past life was hit and flew from Mars, let's say, it could hit Europa or something like that. And then if it made it into that liquid water, maybe life could be sustained there, even if it hadn't started there.
Where, if oceans aren't the best place to start life, where would they be?
We think on the surface of a planet like Earth, right, where you have ponds and lakes and streams. They're exposed to, energy from the sun, ultraviolet light. Ponds can, and in volcanic areas, like Yellowstone, right, where you have geysers and hot springs, right, things can get concentrated when little puddles or ponds dry up. We think those kinds of environments are where life got started.
Things that allow for changes that especially can lead to concentration, like freeze thaw, wet. Dry, wet, and so on.
Can I ask you, when we think about life, Jack, you had said we like in Mars, we would expect that life to mimic or be similar to some of the things that we know of here on Earth. When you conceptualize what life might look like, on another planet, another body, does it always take the shape of things that we know of here? Is it possible for it to be silicon, or like I have no idea. Like, what does life look like? Are there ways that we wouldn't begin even to imagine? I guess is my question. Like, how do we even conceptualize what life would look like if we only have this one planet, Earth,
right,
to understand what life looks like here?
Yeah. No, it's a great question, right? We know a lot about one way that life can exist and can work, and so mostly what we and everyone in the field has been looking at is how do you get to that kind of life, right? So we have a better and better understanding of that. We've only in a very few cases tried to look at variations on that, sort of closely related types of molecules, and so far we find that they don't work, right? They don't have, for example, the right ability to do replication like reactions. That doesn't really address the question of whether some very different kind of chemistry could give rise to a different form of life. That said, carbon chemistry is pretty special, just because of the variety of different types of molecules you can make. Silicon, this always comes up, but I'm pretty skeptical that you could have the range of the right kinds of molecules based on a silicon type of backbone. So I think if we do find life elsewhere, it'll be carbon-based, it'll work in water as a solvent. But, we should keep our minds open and, look around and be aware if there are other possibilities.
One, I will mention, we have a chapter in the book which is called Life as We Don't Know It. And we mentioned studies about the possibility of having silicon. Because there is a group of people that actually try to look into this at some depth. And the final sentence there, they conclude that at the end, carbon does the chemistry of life, silicon does the chemistry of rocks.
Yeah. I mean, there's another good example, right, which is the huge lakes that you see on Titan, right, the moon of Saturn. And I mean, the photographs are just amazing, right? You can't help but wonder if there could be life in that kind of environment. Very different, very cold, very different kind of solvent, like liquid methane, basically. And people got very excited about that, but so far that possibility looks extremely remote because it's very hard to dissolve very much in liquid methane. So if you can't have a lot of dissolved compounds, then it's hard for anything interesting to happen. So that was another example of something that looked interesting, but then you start to think about it and do some experiments and test the ideas, and it doesn't look so good.
We talk about the need for the sun. Earlier, I asked you about the necessaries part. Like we need to be able to get onto the surface and have the sun's rays power, things like that. We're talking about moons, talking about Titans off of Saturn, which is way far away.
Mm-hmm.
And yet there's liquid water, correct?
Yes.
There's right. So
Titan and Enceladus, all these have large bodies of water deep underneath.
Okay, so I had two questions. First and foremost, Jack, I think we're missing out on the big one, which is I want to know what it's like to fish on these planets with all this water. But are these? Does that tell us about the makeup of that body of that moon? Is it heated by the core then? Because it's so far from, like, how does this work?
It's heated by tidal forces. It's heated by tidal forces as this planet moves around, let's say, Jupiter or Saturn. The gravitational force of Jupiter or Saturn and so on exerts tidal forces, like the moon does on Earth. Only there, it's a stronger tidal force. And as the planet moves around, let's say, so it's stretched a little bit by the tidal forces. But if, for example, the orbit is even slightly elliptical, then it undergoes stretching and releasing. That produces heat, and that heat actually generates the liquid water, as opposed to the ice that's on the surface.
I want to ask you, Mario, you mentioned that you had worked on Hubble for the longest time.
I did.
And I'm thinking about the limits of our own technology, about if we go far enough back in time, what would Galileo have done with modern technology? What could we now do with technology 100, 200 years from now? This is a great frustration of mine when I think about these things. What's out there? Like, what are we using to see these spaces? And are you monitoring the advances in what's the next best thing on the horizon that's going to tell us what's out there?
The next best thing, I think, is something called the Habitable Worlds Observatory, which with some luck will be launched around 2035 or 2040. And that will be something that will try to identify, with some luck, a few tens of Earth-like planets, and not only to image them, which we currently cannot do for such small planets, but also characterize the atmospheres of these planets. Now, by the time we will have a few tens of these, and we will look, let's say, for biosignatures in their atmospheres, we will either find something, which will be fantastic, or we will not find anything, but which will also enable us to put some meaningful constraints on how rare life may be. We will be able perhaps to say, even if the conditions are right, in less than 1% of such planets, life manages to arise. So that will be I think, the next big advance in this area. 100 years from now, I cannot tell you. I have no idea what we will be able to do 100 years from now.
But the idea of directly imaging Earth-like planets around other stars, it's really tantalizing, right? It's the technology to do that
it's teasing, is what it is.
But it would be so fantastic.
The stability required for such telescope is just phenomenal.
Yeah.
Well, I think that kind of gets down to one of the frustrations for me is because I see these planets, of course, I'm just a passive science fan, if you will, right? But the idea of once we've identified Earth 2.0 on some other place, now how do we get there, right? Because that's the first thing, it's that is immediately the thing. And I guess that's one of the great frustrations for me of humanity is that we've got 80 good years.
Yeah, right. And that's...
Well, the ones that we actually can really study are the ones, of course, that are not that far away. Mm-hmm. By not that far away, it still means a good few light years. So it takes a long time to get there.
And totally different technologies to get them within even several human lifetimes.
Yes.
Actually, so can I ask you about this? And I don't know whether this falls into the parameters of your research, but I had Kelsey Johnson on the podcast a few months ago, and we talked about interdimensionality. And I wonder about the idea of like monitoring and looking for these spaces and things like that. If we're just limited in our understanding just because of our own limitations of what we can observe and things like that, and then of course what we can get to if we can even find that space. Does that play into the work as well, or no? Or is it just this is what we've got and we're going to move forward?
Well, we can only work with what we have. I mean, this goes without saying. You asked previously about colonizing Mars.
Yes, sir.
I actually have an opinion about this, and it's my personal opinion. My personal opinion is that governments should not continue to invest incredible efforts into crude spacecraft going places. And the reason I say this is that these are, first of all, extraordinarily expensive. The risks are enormous. And the general public doesn't have the stomach to suffer many deaths of astronauts. I mean, you look at the Challenger disaster, the Columbia disaster, the public reacts very badly to this. So if one wants to continue with crude spacecraft, that should be left to private companies that can find people who, are willing to risk their lives and do that. I think that what governments can do, and can do it well, is continue with machines, with robots.
Yeah.
I mean, robots are getting better and better all the time at doing the kind of things that humans can do. So, if you want to do a colony on Mars, send a whole bunch of robots there that, will do all kinds of things. They can do great things. That's my personal opinion. I'm not seeing, NASA sending 1,000 people to Mars. I don't see a particular reason for that.
I mean, for exploring all the places in our solar system, robotic exploration is so much more efficient, right? It's cheaper. You learn a lot. You can change the mission parameters very quickly. Sending humans, though, it's different. It's inspiring to have humans going out and starting to explore the universe. So there's maybe some balance that needs to be struck there. I think we should do the robotic exploration first, but we should be thinking. I do like the idea of thinking of humanity going out there and exploring.
Can I ask you, when we look at these things, I spend more than a fair time looking at the military budget of the United States, going, "Wow, we spend a lot of money on making bombers and warships and X, Y, and Z." Right? I get this impression, gentlemen, that our science exploration funds, whether it's Earth-based, like the work that you're doing, Jack, or Mario, looking towards the heavens, doesn't feel to be like we're adequately spending the money to do this research in like a really, at least on a social scale. Am I wrong? Like,
I don't think you'll find any scientist who thinks that we're spending too much money on science.
Or historian, I can tell you that much. Yeah, right?
People used to ask me whether the Hubble Space Telescope was worth $10 billion that it ended up spending eventually. And my feeling was, I don't know about now, but that was at the time roughly the cost of something like 3 Trident submarines or something like this. Now, if you ask any scientist if they would rather have the Hubble Space Telescope or 3 more Trident submarines, I know what the answer would be.
Guys, I want to ask you this. Because I think the easy question to ask you is whether or not you think there's life out there. But I think the more interesting question to ask you this of your own humanity is this. Do you want there to be life beyond the solar system? Do you want to confirm? At the end of the day, when you've done your work, are you hoping that there is life out there on a personal level, or are you content with being the only one here?
I'll let Jack answer first, and then I'll tell you what I think.
This
is the pre-beer question.
Yeah. When this question about life out there comes up, I always say, well, we don't know. The reason why we're doing all the work we're doing is to find out. And I think it would be much more interesting if there is life out there. I don't know if there is or not, but I think it would be nice, if we do find signs of life out on other planets. That would make me very happy, actually.
Yeah, I would also like there to be life elsewhere. I've over the years become a believer in what we now call the Copernican principle. Copernicus told us that we are nothing special. He was the first to say that. We're not the center of the solar system and so on. Since then, things have evolved to encompass more and more such things. The solar system is not at the center of the Milky Way galaxies. There are lots of galaxies in our observable universe. In fact, probably the estimate is around 2 trillion such galaxies. And there are even theorists who think that maybe even our universe is not one, but there is one of an ensemble of it. So in all of these things, from a physical perspective, purely physical perspective, we have become smaller and smaller. But from a knowledge perspective, we have actually expanded precisely at the rate at which the universe has expanded. Because, it's Copernicus who discovered that this. It was Harlow Shapley who discovered that we're not the center of the galaxy. Hubble discovered that we're not the only galaxy around, and so on. So humans have been at the center of this knowledge, but smaller physically at every such step. So I would like there to be life in other places, perhaps even in many places.
I hope so too. We started off talking about the Arthur C. Clarke quote about life and all these things in the world. It's just too damn big, and I don't want to be. Even if we never talk to anybody, I want to believe. I guess that's where it comes down to this question of facts and truth and belief. I don't know. It's like I want to believe there's something there.
I just think the universe would be a much more interesting place, right? If it's filled with life and all kinds of different forms of life, there'd be a lot more out there to discover.
But, the good news is that we don't have to believe. We're doing the work.
Yeah.
We're trying to find out.
Yeah.
Awesome. I think that's the perfect way to leave this. Mario, Jack, I have to tell you, I just loved the book. I really love how you wrote it. I love that you challenged the readers to rise to the level of the work and not just spoon. This is really, I remember as I turned pages, I'm doing the work as I was reading this. And I know that I was the target audience of really someone who was interested, but not an expert, and then being asked to play along. And I I really got to commend you guys on writing a book that is both accessible but also challenging. I think you walk a really, really great line here. I really love the book. So more than that, I really enjoyed the last hour. Just getting to talk to you guys. I appreciate you guys taking the time for us to find this time today. So thank you so much for being here. This was a real joy for me.
Thank you.
Thank you very much. It's very nice to hear comments like that after working so hard on this book.
Please let us know when you post it or something so that we'll see the link.
Yeah.
Oh, absolutely.
Yeah. Great.
All right. Hold on just a sec.